Okay, so I don't think I'm going to have time tonight to make a full video of this, so I'm going to kind of do an abbreviated version here. So what I did was I scanned in my key, and obviously that way you can pause it and follow the work if you need to. But the reason I did this was so that all the work is there, and then I'll just kind of explain everything as I go through. So like on this first example, hopefully nothing too tricky, it is a simple pendulum and not a physical pendulum, so I don't have to worry about the moment of inertia or anything like that. Right, so if both the length and the mass are doubled, what is the new period? Well, the period equation for a pendulum, right, is just 2 pi radical L over G. The mass does not actually change that number at all. It doesn't change that value at all. So by doubling both the mass and the length, the only thing I'm actually changing is the length, which then multiplies it by a new factor of radical 2. Right, so option C is my correct choice for that first question. Right, so again, feel free to pause if you need to, but I'm just going to keep moving to save us all some time. Okay, so question 2, kind of talking about the resonance, the very last thing we saw in section 8.3. Right, so for question 2 here, if you're designing a building, what do you want the relationship to be between the natural frequency of the building and the typical earthquake frequencies? Well, you don't want the frequency of the building to be the same as the earthquake frequencies, right? Because if it was, then as the earthquake happens, the building would resonate at that frequency, and kind of like, again, we talked about in class, that would be when the building would suffer some structural damage, right? So option B is the best one here. The natural frequency of the building should be very different, should be as far apart from the typical earthquake frequency as possible. We don't want it to be the same thing because that would definitely cause damage. We also don't want it to be anywhere near being the same thing, because what if you had an atypical earthquake, right, that maybe produced a different frequency? Okay, so you don't want it to even be close to the normal frequency of an earthquake, right, because that way you're running the risk of structural damage. So option B again is our best option for this question. So continuing on into question 3, and hopefully question 3 is not too bad. So 3, 4, and a couple of these other questions, right, have to do with the damped motion. But again, hopefully you guys agree that there's nothing too crazy tricky about these questions. So they give us the mass, they give us the frequency, the angular frequency I should say, so they give us the omega of 0.261, and then the maximum displacement of 0.2 when time equals 0. So the significance of the 2 meters, excuse me, not 0.2, but 2 meters when its time equals 0, tells me that the phase shift would be 0, right, because if I'm starting at the maximum displacement, I'm not starting anywhere else in my motion. So the phase shift would be 0. And then really as soon as I set up this equation, it's a pretty easy number game, right? So my position as a function of time depends on the amplitude times e to the negative bt over 2m, cosine of this function. And again, at this point, we actually have all of the variables. So as soon as I identify that relationship, it really is just a matter of plugging the numbers in, right? My amplitude of 2, my time here, which they gave me, or excuse me, my constant b, which they gave me, times the time, and then divided by 2 times the mass, again given, and then the angular frequency. Really the only conclusion you have to realize there is the angular frequency, again, is not my f, it is my omega of 0.261, right? So I've got all these measurements to plug in, and just make sure you are in radians when you plug this in, and that's where I got my position function as 0.502. So continuing on then with question 4 here, right? So again, question 4 is very similar to question 3. The only difference is in this case, because it's just talking about the maximum displacement, I actually don't have to worry about the cosine function, right, since it's just the maximum. So instead I'm taking the cosine to be 1, since it'd be that amplitude at cosine 1, so again that function is gone. So as soon as I set up this relationship here, hopefully this question is pretty easy, right? So my maximum displacement would equal the amplitude times e to the negative bt over 2m. Once again, if we identify most of the information here, we've got the mass, we've got the time, we're looking for the constant b. So we have the mass, we have the time, we're looking for b. The only conclusion we have to reach here is, again, it's 1/3 of its original amplitude, right? It's 1/3 of the maximum displacement. So if this is a, then on the left-hand side, the maximum displacement would be 1/3 a, which then allows me to cancel the a's out, allows me to do a little trig, right? So, excuse me, not trig, but it allows me to use the ln function on both sides to then get rid of the e, right? And then from there, it's just, again, some algebra to solve this the rest of the way. So about 30.52 kilograms per second is what we end up getting. And notice the units there, the units for our constant are kilograms per second, which makes sense. if you think about this being time, so kilograms per second times seconds would cancel out seconds, and then you'd have kilograms divided by kilograms, which would leave me with just a coefficient in the power there, which is exactly what I want. So anyway, continuing on then to question 5. Right, so question 5 is actually maybe a little bit easier than initially we might want to make it. Right, so they give us the angle as a function here, and then they ask what is the length of the pendulum. Well, the reason this is actually a little bit easier is even though they give me this entire function, really the only part I care about is that coefficient there with the t. Right, it's that omega t that I'm going to focus on. Right, and I can choose that part of the function to be either omega times t, or 2 pi times the frequency times t, which is what I did, or 2 pi divided by the period times t, which is another option as well. Right? But anyway, I chose the interior of this function here to be 2 pi times the frequency, right? And then that way 2.85 equals 2 pi times the frequency. That allows me to find the frequency about 0.454. And then once I have the frequency, I just use the frequency period equation, right? So the frequency, which is the inverse of the period equation for a pendulum. And I just plug in to get 1 over 2 pi and then square root of g over L. Since I know the frequency, since I know the acceleration due to gravity is 9.8, it's now just a matter of solving for that, and I get the length to be 1.21 meters of length. So again, this one originally maybe looks kind of intimidating because they give us a whole function for it. But if I just solve for the frequency by using the interior of that function, this question becomes pretty easy to then solve the rest of the way. Which brings us then to question 6, which is probably, in my opinion, one of the tougher questions on here. Sorry, I zoomed that out so we could see a little bit more here. And I'll get to this then in just a second. But right, so this is probably one of the trickier questions in this homework. Okay, so with this question, and this is definitely one of the questions that I wanted to make sure I could explain my key for, because I know I kind of jumped around all over the place, and as you can see, I tried some things, and even I had some trouble starting this. So I imagine a lot of you, as you first looked at this, were probably thinking some of our new equations for damping, and maybe didn't start this off as simple as we could. And so for part A, they actually just ask what is the magnitude of the acceleration of the block upon its release at x equals this position here. And actually, if you look down here, if you notice down here, right, to find that acceleration is actually way easier than I was trying to make it. To find the acceleration, I just need to know that the net force comes from the spring force, and then plus the resistive force, right, D, the drag force, if you will. But in this case, the drag force, which they tell us is, in the problem, they tell us is proportional to the velocity, right? So regardless of whether I think that is negative b times v or whatever, it does tell me in the question up here that it's proportional to the velocity, right? So because when it's first released, the velocity is 0, the drag force is going to be 0. So my initial acceleration, right, when we first release it, is just going to come from the net force equal to the spring force. And since they give me the spring constant and they give me the displacement and they give me the mass, it is as easy as plugging in those measurements and getting about 17.2, right, 17.175. So again, part A of this question is actually very, very easy as soon as you simplify it, right, and avoid trying to do too much with this. So then part B is where it does get a little bit more challenging, and there are a couple different approaches you can take to this one. So like I said, I wanted to kind of go through and justify the approach that I took, but there are actually a couple different methods, and they all should get you about this same answer. It may vary a little bit depending on where we've rounded, but again, it should be pretty close, pretty comparable to that same thing. So here's what I did. I took advantage of our new equation that says the maximum energy at a certain time would be equal to the initial energy times this decay factor, right, this e to the negative t over tau, right? So if I'm taking that relationship, then I just need to try and figure out what some of these values are so that ultimately I can find tau, because if I can find tau, I know that tau is defined as mass over b, and so if I just take that relationship, then I can pretty easily solve for b. So all I had to do was find the energy at that specific time, find the initial energy, and that's what I did over here to the right. The initial energy would be based off of the initial potential energy of the system, so 1/2 kx squared, which ends up being about 29.5 joules. The energy at that specific point in time, well, they tell me that the velocity is 2 or negative 2 meters per second when it reaches that position for the first time, right? So because of that, I can find the kinetic energy of the system at that point in time, which would be the total energy of the system, right? So 1/2 times 5 times 2 squared, which is 10 joules. So then I took those measurements and I plugged those in over here for my energy, my initial energy and my final energy, right? So that's where the 10 and the 29.5 are coming from. So then the question became, okay, what can I do with my time, right? What can I do with the period here? So I found the period for the spring system based on the mass and the spring constant, right? So I plugged in my mass of 5 kilograms, I plugged in my spring constant of 125, I calculated this number and I got 1.26 seconds. But the amount of time that it takes to reach the equilibrium position for the first time, which is what we're looking at, would only be a quarter of that total period, right? It'd be a quarter of the motion. I start at the amplitude, I go to equilibrium, to the other amplitude, back to equilibrium, back to the other amplitude, right? So I divided that time then by a quarter. I took a fourth of that total period, and then that period was my time that it takes to reach equilibrium. So then all I did from here is I again plugged in those measurements and solved for tau. So I plugged in those values, solved for tau, and then once I had tau, I set that equal to the mass divided by b, and I solved for b. Right? So again, take your time and look this one over. This is definitely one of the trickier questions. So if you do have questions on this, let me know. Again, I will be in early tomorrow morning if you guys need me. So if you need further explanation, let me know. But all I did again for part A is taking advantage of the net force, which I know the drag force would be 0 at that location. And then for part B, I was taking advantage of my energy relationship here for when damping is in effect. And I found my initial and my final energies. I found my period and then the time that it takes to reach the equilibrium position, and then solved for B. So while this is a very challenging, a very good question to look at, hopefully by the time you're through this explanation, it's not too bad in seeing exactly what's going on. So then without further ado, moving on to question 7 here. So question 7, a long, thin, uniform rod of length 1.5 is to be suspended from that frictionless pivot point at some pivot point along the rod, so the pendulum takes 3 seconds, right? So the period is 3 seconds. How far from the center of the rod should the point be pivoted, right? Should it be pivoted? So since they tell me the period here is 3 seconds, right, I'm going to start with the period function for a uniform rod. So again, notice this is not just the square root of L over G. It's the period of a rod that has a certain mass, so we have to use a physical pendulum. And that tells me then it's this period of 2 pi times the square root of I over mgl. Right? So the trick to this question then becomes, they don't give us the mass, so how can I represent the moment of inertia in terms of the mass? Well, the parallel axis theorem, right? This is what I'm using down here on the left-hand side. The parallel axis theorem says the moment of inertia for the rod would equal the moment of inertia of the center of mass, which is the 1/12 m times 1.5 squared. This is my 1/12 m times the total length of the rod squared, plus m times the length being the distance between the pivot point and the center of mass, right? So that L is what I'm ultimately looking to solve for. So all I then did was solve this in terms of m, right? So I went ahead and simplified this to 0.1875 m plus L squared m. And then notice I went ahead and I actually factored the m out of both of those. So my moment of inertia equals m times this quantity here, right? So the 0.1875 plus L squared. Then I just substituted that into my equation up above, and at this point I let the algebra take over. So my period equals 2 pi times the square root of m times that moment of inertia there, divided by mgl. Obviously the masses, the whole point of factoring the mass out is it can now cancel out. So I end up with the remaining part of the moment of inertia on top, the 0.1875 L squared, and then divided by g times L. At this point, we do end up with a quadratic equation, right? So I had to multiply both sides by 9.8 L. So I had to multiply both sides by 9.8 L, and then I get my 2.234 L equals 0.1875 L squared. I get everything to the same side, and then I do have to do the quadratic form. Now when I solve the quadratic formula, I get two possible answers. I get either 2.147 meters or I get 0.087 meters. Now hopefully the obvious problem with the first one there is 2.147 meters is longer than the actual rod itself. So it's not possible for us to have a pivot point that's located further than the actual rod's length away. Right, so that one I went ahead and ruled out. So then my only remaining answer is the 0.087 meters or 8.7 centimeters. Right, so anyway, this will be the last question I get to in this first part of the video. Hopefully following my work here on the keys hasn't been too bad. I think it is saving a little bit of time here, so hopefully it's easy enough to follow still. And by all means, feel free to pause and go back and check any of these if you need to.